So we ended up with the gradient, and we showed that delta t is equal to integrate delta t along the points A and B. These are points in XYZ coordinates, so they might have 3 components. It really doesn't matter. Delta t is equal to gradient of t dot dl. Along the curve. Much more can be said than along the curve, but at the moment, just along the curve. Well, I say much more can be said than along the curve. Well, you might ask, what is delta t along this curve? Is that the same as, because the end point and beginning point is the same? I will show that that is in fact the case, but we haven't seen that yet. Given a curve, delta t is given by this expression. Okay, and what did we do last time? We talked about the area integral. Here, along any surface area, we defined the area integral of a vector to be A dot dA. At least abstractly, we can write it this way. Well, what does A dot dA mean? It means if you look at a small differential area, well, whatever that means. We'll clarify what that means. But I'm writing this as a vector. So what do I mean? How do you make it a vector? By defining a normal. Okay, so it's a vector whose magnitude is the small differential area, and the direction is the normal vector. Now, again, then very quickly we talked about, well, which normal vector? You can have normal that way or normal this way. In general, the context will have to make it clear. Or in the case of a closed surface. In the case of a closed surface, what do you use always? The outward normal. Okay, so what I want to get to is divergence theorem. So let me go ahead and just do. Oh, I think I didn't pick a vector A. It really doesn't matter. I picked a vector V. So let me do this for a standard example to lead us to divergence theorem and also to define what is a divergence. So I have an example of a vector, and I believe this is, I'm not creating more and more vector fields, so I think it's the same vector field we got by taking the gradient of some function last time, 4x plus y, x hat, plus, recall if this was true, x, y hat. What I'm going to do is integrate this vector field along a closed surface. Well, and because we are doing Cartesian coordinate system, closed surfaces are generally cuboids. And hopefully, if not today, the next day we'll get to other coordinate system. And I won't make it very interesting. I'll make all sides one unit. Let me put an axis. This is x. This is y. And this is z. As we do this example, I want you to, mine is only a two-dimensional drawing, so I want you to think of this as the x-axis, this side of the table, this as my y-axis, this as my z-axis. And imagine a cube sitting here. Now, I'm doing an area integral, which means I have to integrate over all the surfaces of the cube. How many surfaces are there? 6 of them. Okay? So, and it's a closed surface, so the cube I'm going to pick is going to be, I'm sorry, the normal that I'm going to pick is going to be?
On each face, the outside.
Every face, the outside normal. So I'm going to label each side, and hopefully you understand by my perspective. I'm going to call this side surface 1, and then below I'll call it 2. Then I'm going to come over here. This is going to be surface 3. This is going to be surface 4. Well, let me do first the 4 sides, and then we'll worry about, we have this side left and that side left. Okay? So let me do V dot dA along this face. So this is in the XZ plane. What is my area vector? Tell me the differential and then tell me the outward normal. Let's pick the easy one first. Let's pick the outward normal.
Negative y hat.
Very good. Negative y hat. Now, what will the differential, its area, so what are the 2 axes along that plane? X and Z. So the differential would be dx and dz. So meaning if I pick a small little triangle over here, this is dx, this is dz. That's great because all I need is the y component. So again, I'm going to put it as 1. I'm going to put minus y hat dot y hat is going to be 1. I'm going to get minus x dx dy. Correct? Now, in the x, am I correct? Please make sure. Okay, so let me continue here. Now I'll show you that this is a double integral when I write it this way. So I should really write it as minus and I would get minus, let me do this one first, 0 to 1. X dx 0 to 1 minus 1/2. Please verify. For my area 2, V dot dA, what is dA? First of all, what's my outward normal? Melissa, outward normal. Negative C, good. Negative C hat. And what's my differential? The area. dx dy. Okay. So I'm going to stare at it, and you're going to tell me how I computed the integral so fast. There's no z component. There's no z component. This vector field does not have a z component. That kills it. now let's do, okay, let's do this very quickly. The normal vector is now again what? Positive y hat, right? So can I write v dot dA to be equal to x dx, or no, dz, right? I have this little rectangle. This side is dx, this side is dz. Did I make a mistake in one?
I think it's
dz, correct? I even wrote it correctly, dx.
And you had to define that as dA is equal to dx dz, and then
Then when I copied it, yeah, dz. And for that exact same reason, I think I get plus 1/2, right? Let me check my notes so that we're not making a mistake. Okay. And then 4. What is area 4 going to be?
second to 0.
Yep. Why is that? It's the same reason as that. There's no z hat component. So I have to label 2 more sides. Yeah, we're done with all these sides. So I'm going to call the front side 5 and the back side 6. So let me do it this way. Chip, what is my dA vector? And what goes here? dy dz. And therefore, I'm going to have to write this as, it's the x component, 4x plus y dy dz. Yeah? Now you might go, again, wait a minute, this is kind of weird. It's dy dz, what's x doing over here? On the front face, what's the value of x?
Always 1.
Always 1. So, and I don't see any z here, so first let me do z. So this is 4y plus y squared over 2, 0 to 1. So that is 4.5. 4 plus 1/2. Okay, we have one more integral left. The backside. The only difference in the, well, there are 2 differences in the backside. First of all, my normal is going to be minus x hat. And then 4x plus y is a dy dz. Except what's the value of x on this guy? On the back surface? On the zy plane? 0. I'm going to bring the dz, and then I'll have y dy 0 to 1, 0 to 1. So that's just minus, then I have, well, minus, this is going to be 1, this is going to give me 1/2, because y, integral of y is y squared over 2, when it goes from 0 to 1, it's just 1/2, and I get minus 1/2. Not difficult, but you have to keep track of things, right? So this entire course is that. Okay? E&M, it's not difficult if you keep track of things, because it's still within the realm of classical mechanics, and we can sort of intuit. We have this natural intuition of vectors and whatnot. That falls apart in quantum mechanics. You'll have to redevelop intuition, that's all. Okay, we set out to integrate a closed surface that we broke it up into 6 surfaces, so therefore I can write the closed surface, the integral of v dot dA, equal to, do you recall all the non-zero ones? I had 1/2 plus 4.5 minus 1/2 minus 1/2. Is that true? So what I'm going to do is I'm going to write, I should have never over there, but that was the natural ending. This is what we will need. Because what I'm going to do now is talk about the divergence theorem. The divergence theorem has to do with an integration. And this is the problem we're doing. So let me state the divergence theorem, and then I'll continue with the example. The divergence theorem is very, very powerful. You know one side of the divergence theorem. It says the area integral of a vector field on a closed surface, on the boundary of the closed surface, should be equal to the integral inside the volume. Always remember I talked about fundamental theorem of calculus. It relates a derivative in the inside to the values of the outside, just like the fundamental theorem of calculus. This is just fundamental theorem of calculus in 3D. Now, if I were doing physics, I would call a volume integral dV. This is the only place where I'm not sure why Griffiths chose what he did, but he uses d tau. D tau is nothing more than dx, dy, dz. Well, it's the integral on the volume of some quantity. That some quantity is the divergence of v. Let me write the symbol first, and then I'll define it. This is what it is. We don't have to know. Well, I'm going to define it. Is referred to as the divergence of V, and is given by the gradient. Well, this is the gradient dot I mean, just as it's written, V, but let me define it. I'm going to define it on the other side, huh? Because again, I want to hang on to this. What is the gradient?
Del x x hat.
Yeah. Y hat dy plus E. So this is bound to happen. Equations are invariably longer than the board. And then when you carry it out, that is what should go in here. That is the divergence theorem. And this is the definition of divergence. You guys are awfully quiet. Please ask me a question. You know, I'm awfully happy when I use a pen and it's out of ink. This is my chalk from day one. My new stash. But there's a sense of satisfaction in it. So the question is, how many chalk worth of physics are you going to learn this semester? Question. Let's illustrate the problem by doing an example. It's very simple because I don't have to integrate 8 times. But we just have to recall the divergence theorem. Example continued. So for the previous example, I'm doing now for this same problem. What is the divergence? Take the x component and take the partial derivative with respect to x. What do you get? 4 plus take the y component and take the partial derivative with respect to y. 0. Well, this couldn't be easier, right? We have not proven the divergence theorem, but it holds every single time. James, you good? Fantastic, right? But this has to be true. I'm sorry?
It beats the cube.
Beats doing the 8 surface integrals. But let's look at what this might mean. why do we call the divergence the divergence? It really comes from the divergence theorem. So I'm going to state it one more time. I don't need this anymore. So it says the divergence of any vector field, smooth vector field. By smooth I mean differentiable, twice differentiable, continuously differentiable. dx, dy, oh, Griffith's notation, d tau, is the closed area, the boundary of a three-dimensional solid surface is a closed surface. Now look at this. This area vector is, so let me draw a closed area. Let me pick an arbitrary. And V, I don't need mine, you can point in any direction. So when I do V dot dA, it's the amount of V flowing out of the surface. If V is a vector field that describes flow of rain, and your windshield is your surface that you're talking about, in this, say your front windshield, then V dot dA really determines the amount of rain that falls into your car. Well, if you pick the inward normal. Okay? So V dot dA is the flux. In this case, the amount of V that flows out of the surface. So the divergence per unit volume, this is when you integrate the divergence. The divergence is the amount of vector field that flows out of the surface per unit volume, divided by volume. Does that make sense? Amount that flows out per unit volume. Hence the term divergence. So if this is positive, there is stuff flowing out. Think of it like water from a sprinkler. If it's negative, things are flowing into it like a sink. So that's we sort of discussed the math and the physical interpretation of divergence. So you can write that sentence down if you'd like. The divergence measures the amount of vector field flowing out of a surface for every unit volume of the object. Yeah. Because this is this times volume equals that. It's not a very mathematical statement, but it's a very intuitive statement. It connects you to what we're about to do. Okay, well, you probably guessed it at this point. If we're going to talk about divergence, we're going to talk about curl. Curl is like the cross product.
Curl theorem?
Yes, it's called the Stokes theorem.
So a negative value for that would mean that it's flowing in?
Flowing in,
So it's like
yeah.
a sink?
Yeah, it's like a sink. Yeah, a source versus a sink. The divergence, I'm glad we use that terminology. Divergence creates a source. We will see very soon that, and you have seen this probably in freshman physics, divergence of the electric field is rho, it's Gauss's theorem, by the way. Rho over, we'll cover this. That means the source of the electric field is charges. That's what it is. Okay. This is the only way I curl. Denoted like so. It's a cross product. It's the gradient crossed with the vector field. So it's a cross product. We first write x hat, y hat, z hat. And then I have to write gradient. Physicists or mathematicians, we're incredibly lazy people. This is too difficult for us to write. So we'll shorten this to that. Beats the same thing. It fits in better. Well, you know what that means. Start off with the x hat, open parentheses, this acting on that, minus this acting on that. Then, because it's the second one, you put a minus y hat, dx acting on what? James?
So you just asking for what it's multiplied by?
Yes. Not multiplied by, acting on. It's a partial derivative. It's taking the partial derivative of some function. Which function? dz, good. Minus dz plus z hat. Alyssa? So you know, I'm going around the room like this. What's my z component? What's the first term that I'll write? I'm sorry? So I wrote the x hat component. I wrote the y hat component. Now I'm writing the z hat component. Okay? So then how do I finish this off? Del y?
Do cross products like this.
You do it a different way? But it is important to do it this way because see, it is this guy, right? So you ignore this row and this column. And then go this to this minus this to this. That's what we do every single time. If I'm doing this one, I do this to this minus this to this. Okay? So I have dx minus yeah? That's the curve. Let's take the curl of a vector field and then use it in Stokes' theorem. You'll see Stokes' theorem in Ampere's law. So I picked a different vector field. I do these examples before I come to class. That way, if we do something grossly wrong, if right-hand side is not equal to left-hand side, we don't have to sit and scratch my head. You know, I can just see where the mistake is. I think I lecture, in my opinion, very slowly, so I could use like 10, 20 more lectures this semester. Now, you guys are probably thinking we could do with 10, 20 less. That's okay. I'm not boring you guys to death, right? I'm not so slow where you're going, oh, this is just, yeah.
I don't think you're slow. You're kind of fast. Not that loud. Like not fast that I can't keep up, but
Yeah.
like.
Well, that may be true. I feel a sense of urgency for no reason. I feel like pressure to cover more. But good news is, if that is indeed the case, you get to revisit it.
Right.
You know, there's time travel allowed in this course. Just watch the video. So please check, because I'll be using, this has to be correct, not just as an exercise. I'll be using the Stokes theorem very quickly. So I'm going to put 2x y squared z y x squared. You know, all the research done by people who do education research says YouTube videos have to be 6 minutes or less. And they, chide me in a good way. Say, your videos are too long. I don't know what I can do in my...
But you make a different kind of videos.
But, yeah, we can do one problem.
Those are like Mr. Beast kind of people that you're talking about.
Okay, let's do the curve. Okay, please make sure I'm right, huh? I'm taking the partial with respect to y of this guy, minus 3x squared. Then I get 0, yeah? Minus y hat, partial with respect to x, so that is minus 6xy minus 2xy squared plus z hat 2xy minus 4xy z. Can I simplify it somewhat? Minus 3x squared x hat plus up to minus 3 squared, okay, 6xy minus 2xy squared plus 2xy, 1 minus 2z. So also the lesson to be learned is this is 2 and this is z. That's why I put a line. Yeah? And this is 1. I do a little flag there. So this is just a formula. Yeah? Happy with how to take the curve? So we have to do an example. Please make sure you keep up with class and ask questions. I really, honestly, I don't mind. I would like for all of you to make an A. Okay, that is exactly what I'm hoping for. Work hard, and I'll work with you. Stokes theorem. Let me write the theorem first. If I take the curve of a vector field and do a line integral, which means I have to specify the normal, which way is the normal pointing, I get, again, if it's an area, on this side, it'll be the boundary of a two-dimensional surface. What is the boundary of a two-dimensional surface? Boundary of a three-dimensional surface is a two-dimensional surface. Boundary of a two-dimensional surface is a one-dimensional, a curve, closed curve. So there's a little bit of freedom in here I want to clarify. So let's assume here is my area. I can pick two normals. Let's say I pick this one because one affects the other. So I'm picking this normal. So that means I'm picking it everywhere. If I pick this normal here, I can't pick that normal here. It has to be consistent. Okay, so then what's the freedom? And how do I, if I pick the other normal, I'm going to get a negative sign here. So that should correspond to a negative sign here too. So I have two choices in DL. I can go this way along the curve, or I can go this way along the curve. For this diagram, and this is the quintessential example you have to remember. If you remember this example, you can do all Stokes' theorem. The way I have drawn, because of this guy, this is the outside part and this is the inside part. So it's a surface like this. and what you see here is this end of the surface. Okay? So my DL has to be this way. Which means over here. How do I remember that? You pick your right hand and you place the edge of your palm along DL, and you pick your thumb along the normal, then your fingers curl towards the inside of the surface. Yeah? Again, if you remember this diagram, that would be sufficient. So this orientation is included in the statement of the Stokes theorem. And so I picked a vector field and I have the curl already, so we can directly deploy it. And again, we're using Cartesian system, coordinate system, so we can integrate over rectangles or squares and things of that nature. And the very next topic would be other coordinate system. So let me at least finish this. I want to hang on to both of those. So you will have to remember the two sides. So let me draw an area, and it's the expected one. So this is my area. So I need to show you my normal. That way, that already fixes my orientation. Let's do the area integral first. So dA, the normal direction is the z-axis. So then, so when I do the curl, integral of curl across V dot dA, I have my curl here and my dA here, so I can immediately write this as I only take the z component. Yeah? So it is 2xy times 1 minus z, and it is dx dy. Again, when you look at this integral, it looks odd. We're doing dx and dy, so you wonder what z is doing there. Well, easy enough. What is z on that area? 0. So this is 2x dx, y dy, 0, 1, 0, 1. We've done this so many times. Every x dx will give you 1/2. So the left-hand side, yeah, x squared over 2, y squared over 2. It's going from 0 to 1, so 1 over 2. So this is already 1/2. Let me call this 1, 2, 3, 4. Let me do V dot dl through path 1. dl clearly is dx x hat. Yeah? It's along the x-axis. So I just need the x component. And what do I get? minus 3 x squared dx 0 to 1. I don't recall that at all. 2 That's not what I have. What's the x component?
2x squared z. I mean, x, y squared z. 2y squared.
Oh, I took the x component of the curve. That's wrong.
Yes.
You guys are on top of it. As Ashik correctly pointed out, 2x y squared z dot, yeah?
Oh, yeah, you did that.
Yeah, you take the dot product. That doesn't sound right. I have 2xy. Oh, maybe that's a different integral. Where's my Stokes example? I'm sorry? It is 0, right?
Yeah, that's what I like.
Yeah, I like it too, but oh, it is 0. Oh, yeah. Good. What does that mean? What is this one going to be? Why is that? That's also the same component, but it's the minus direction. Still, z is 0. So this is 0 and this is 0. Correct? I don't need the curl of v to get confused anymore. So I'm going to remove that. What's the next path?
2 and 4.
Path is 2 and the it's dy, correct?
Yeah.
So it is y x squared dy, or rather that is y x squared dy 0 to 1. When x equals on path 3, what's the value of x? Equals 1. So that's integral y dy 0 to 1, which is 1/2. Now let's do path 4. What's the only difference? Yeah. Minus y x squared dy 0 to 1, which is 0. Therefore, closed. Zero plus 1/2 plus 0 plus 0. Time is up, so we better have shown that the Stokes theorem is true. What was the area integral equal to? 1/2. Please confirm. Meaning this guy. We should have had this, and then we have this. Those are the two sides of Stokes' theorem. Yeah, so good catch. Don't make the mistake we're just about to make. When we compute the curl of V, that's fine for the left-hand side. For the right-hand side, you use V, not the curl of V. Very good? Step 1, save the chalk. Step 2, erase the board. Huh?